Thank you very much for the introduction, Rafaela. And of course, thank you very much to the organizing committee to invite me to give this talk in this meeting. Today, I'm going to speak about high pressure induced electronic modification in 4F and 5D system by Xray absorption spectroscopy. First, I will present the two complementary techniques that normally I use to characterize materials. Then I will show the experimental setups in X-ray absorption spectroscopy experiments and X-ray diffraction experiments. And then I will present the results obtained for two samples. First, the European sulphide, and second, the Iridium metal. Normally, I use these two complementary techniques. The X-ray absorption spectroscopy is a local proof that allows a chemical selective investigation of the electronic and the local structural properties of the absorbing atom. And X-ray diffraction, as you know, provides information of the average long-range order crystallographic structure. The SAS experiments were carried out at BM23 beamline in the ESRF. Here in the image on the left, you see to carry out high pressure experiment at BM23, we use this micro-SAS station. This micro-SAS station is formed by two KD mirrors to focus the beam vertically and horizontally. And now we can get a beam spot around 2 per 2 square micrometers. After the micro-SAS stations, we place both ion chambers to work in transmission mode, I0 and I1, and of course the pressure cell intermediate. Also, you can see here in the image on the right, the PIR system to measure the ruby fluorescence. Normally in the ESRF, we use a membrane pressure cell. So this cell is connected to an automatic pressure driver, so we can increase the pressure during all experiment without to remove the pressure cell from here. Here you see in these images the kind of membrane pressure cell we use in the ESRF, and you can request them in the high pressure laboratory for your experiments. And concretely in SAS experiments, we have to use polycrystalline nanodiamonds in order to avoid Bragg diffraction peaks by bulk diamonds in our SAS spectra. For my experiments, these nanodiamonds were supplied by Tetsuo Irifune and his group. Here in this slide, you can see the experimental conditions for both experiments in SAS, the European sulphide and Iridium metal. In European sulphide, we measured in European L3H in transmission mode. You see the energy is very low, is lower than 7 kiloelectron volts. So for this reason, we have to use this kind of nanodiamonds in order to avoid as much as possible the absorption of photons by diamonds. Here in this side of the cell, I mounted partially perforated with a thickness of 250 microns. And in this side, I mounted a totally perforated with a mini anvil over with the thickness of 500 microns. So we reduced a lot the thickness of diamonds. The diamond cooled was 300 microns, so we could increase the pressure up to 35 gigapascal. And we used the ruby fluorescence as pressure sensor and ethanol-methanol water as pressure transmitting medium. In Iridium, we measured in Iridium L3H in transmission mode. In this case, we use standard size nanodiamonds. You can see the difference between these normal nanodiamonds and diamonds they are around 1.7 millimeter each. And we could increase the pressure up to 1 megabar. And in this case, we use helium as pressure transmitting medium. The X-ray diffraction experiment was carried out at AD15B beamline in the ESRF. And in this case, we worked with a beam spot around 7 per 7 square micrometer. We use again helium as pressure transmitting medium. we increased the pressure up to 1.5 megabar. Of course, we used standard size polycrystalline diamonds, and in this case, we used copper powder as pressure sensor. Now I'm going to start with the examples. First, the europium sulfide. Why we decided to study europium sulfide? The first reason was because the europium is the most used rare earth for optical application. As you know, for optical applications, for example, luminescence or fluorescence, the local environment around the europium or the rare earth is very important. If the local environment, or for example, the crystal field change, the optical properties will change. Moreover, europium sulfide gave us the opportunity to study europium into different local coordination, because in this sample there is a structural phase transition above 21 gigapascal. So at lower pressures we can find europium 2+, regular octahedral coordinated, and above 21 gigapascal they are coordinated, they are hexahedral coordinated. However, we realized later by optical application the interesting electronic properties of europium sulfide. In the figure B, you see the pressure evolution of the energy band gap, and you see around 14 gigapascal there is a trend change, and here around 21 gigapascal there is a complete metallization. This metallization is concomitant with the structural phase transition. However, if we focus in this point around 14 gigapascal, we see in other europium monoshell coordinate similar electronic discontinuity or electronic anomalies. In europium oxide, you see this resistance drop at the same pressure, 14 gigapascal, and also here you see the reflectivity rise around 14 gigapascal. The reason of these electronic anomalies in europium monoshell coordinate are because of the electronic transition from semiconductor to half metal. However, the basic physics behind of this electronic transition is still unknown. We are going now to reveal the phenomenon behind of this electronic transition by science. Here in the figure A, you can see the pressure evolution of the science spectra up to 35 gigapascal. As you know, the white line associated to europium L3H correspond to the transition from 1s core level to 5D valence levels. So if we do the second derivative of this science spectra, you see in the figure B, we can distinguish the bimodal character of 5D orbitals. This peak, the first peak, lower energy, correspond to T2G levels, and this peak correspond to EG levels. So we can see the crystal field splitting. And also we see as the pressure increases, the crystal field splitting increases. After a Gaussian fit, we can represent the crystal field splitting values under pressure. Before the structural phase transition, we can see the crystal field splitting increases very quickly. If we focus in the trend, in the individual trend of T2G and EG in the figure G, we can see the difference. The energy associated to T2G decreases 3 times faster than the energy of EG. And here we have the reason of the electronic transition around 14 gigapascal. Now I'm going to explain better with the calculated band structure. I calculated these band structures by the software of BAST. So here you see the band structure, and here the electronic density of a state at the first regime before 14 gigapascal, when europium sulfide is semiconductor. And in this figure in the middle, you see the same, the band structure and the density of a state in the second regime, when the europium sulfide is half metal. So if we focus in the band structure, you see the bottom of the conduction band is constituted by T2G. And the black line, continued black line, here you see better, are occupied by spin-up electrons, and the discontinuity line are occupied by spin-down electrons. So if we see the bottom of the conduction band decreases at the rate of 44 millielectron-volt per gigapascal. This value is similar, very similar to this one obtained by SAINS, 38 millielectron-volt per gigapascal. So this decrease leads to the half metallization, and it's half metal because only spin-up electrons occupy the Fermi level. This result is common for the other europium monochalcogenide. Here you see in the image on the right, in europium oxide and europium selenide, we see the half metallization at the same pressure. So this explains the electronic anomalies. And in europium telluride, happens before around 10.5 gigapascal. Another interesting result is europium valence change when the pressure increases. At the beginning, we have europium 2+, but then as pressure increases, we are getting a mixed valence state for europium in europium sulfide. But this result also is common for the other europium monochalcogenide. Here on the left, you can see the europium 3+ contribution is becomes bigger in SAINS spectra for europium oxide, and you see here the mixed valence state for europium in europium oxide. So now I'm going to present the results from the second sample, is iridium metal, and in this case, for the same electronic reasons, we study iridium. In this case, in 2015, Leonid Dubrovitsky and co-authors reported a new electronic transition, and they called this new electronic transition core level crossing. And here you see the pressure evolution of the Ca ratio of the structure of osmium. And this discontinuity was associated to an electronic topological transition, but this one around 400 gigapascal was associated to the core level crossing between 4F and 5P, as you can see in the figure on the right, in the projected density of a state. Later, theoretically, they discovered this new electronic transition is common in the most of 5D transition metals, in rhenium, in iridium, and platinum. However, iridium, as you can see, is a best candidate to study core level crossing because the crossing, as you can see, happens at relatively low pressure, 80 gigapascal. So we decided to study this electronic transition. Before to start with the study of the electronic properties, we decided to study the mechanical stability. And for this reason, we did experiment in X-ray diffraction. And here you see on the left, the pressure evolution of the diffraction patterns. And as you can see, iridium conserved the FCC structure up to 1.4 gigapascal. After level fitting, we obtained the equation of state represented by black dots. And if we extrapolated our equation of state up to 650 gigapascal, we can see our equation of state matches perfectly with those results obtained by shockwave experiments and quantum molecular dynamics. And this reflects the quality of our X-ray diffraction data.
Virginia, a few minutes left.
Okay. So I'm going to finish. And now we focus in the local structure. Here you see the exact signal. After the exact fit, we obtain the neighbor distances. So you see here the nearest neighbor distances and the second neighbor distances. You see in all of them decrease monotonously. We don't see the effect of the core level crossing. So we will see what happened in a sense. In sense, if we have any change, if we see any change in the watt line, for sure the change is related to the effect of the core level crossing because of the interaction between core and valence electrons. After the fit, we calculated the intensity. We obtained the intensity, the width, and the peak position of the watt line experimentally and calculated. And you see, we don't see any effect of core level crossing. All of them are constant. So the reason is because the interaction between the potential that describe the interaction between the core and valence electron is very weak in iridium compared with spin orbit coupling and its crystal field force. So finally, the conclusion, European sulfide, the first example. So the pressure-induced increase of crystal field and leads to half metallicity at 14 gigapascal, and this result can be extrapolated to the other European monosaccharides. And there is an increase of European valence, yielding a mixed valence state. In the iridium sample, the FCC structural iridium is conserved after 1 megabar, and the core level crossing in iridium is negligible compared with the crystal field and the spin orbit coupling. I would like to thank to all my collaborators, especially Javier Ruiz Fuertes, Juan Ángel Sanz, Angélica Rosa, Fernando Rodríguez, Federico Cova, Gaston Garbarino, and Olivier Maton. And of course, thank you very much for your attention.
Thank you, Virginia. It was really nice. We have time for a few short questions, if there are. Otherwise, I have one small.
Okay.
For the European, when I see the discontinuity in the hexanes that you showed, it's a bit later than 14 GPa, like more like 18 or 20, if I'm not wrong. You think this might be due to, I don't know, transmitting medium or, I don't know.
Here?
Yes. I mean, the change of slope is a bit later.
Yes. The crystal field, the slope of the crystal field changed because of the structural phase transition.
Ah, okay, so this is another thing.
Yes, here in European sulfide and the other European chalcogenide, we have two electronic transition. Okay. So the first one around 14 gigapascal and the second one around 21 gigapascal. And the 21 gigapascal is the complete metallization. Okay. And both is because of the crystal field splitting rise.
Okay, thank you.
Welcome.
Other questions?
Rafael, I have a question, if possible.
Yes, please.
Just in this presentation, I missed one point that the Virginia linked the crystal field splitting energy with the features of the second derivative. No, I missed the reason that how it can be linked. I believe Virginia has a reason for that, but I would be very happy if she can explain me the principle to link this the feature in the second derivative and the crystal field splitting energy.
Okay. So the watt line we are measuring European L3H. L3H. So L3H is the transition from 1s to 5d orbital. So in the watt line we are seeing the empty 5d valence levels. You know, 5d levels are splitting in two levels, T2G and EG. So if we do the second derivative, we can distinguish this B-model character of 5D orbitals, as you can see in the figure B. And we can study the pressure evolution of both peaks.
Okay, thank you.
Okay.
Thank you.
Okay, thanks again, Virginia.
Okay, thank you very much.
And let's move to the last speaker of this session. So Fabrice Wilhelm from ESRF, who will talk us about magnetism of unconventional superconductor UG2 probed by high pressure XMCD.
Okay, thank you, Rafaela. So the talk that I will present today is the outcome of a long-standing collaboration between 3 different groups, namely the ESRF beamline ID12, whose responsible is André Rogalev, the team of Jean-Pascal Brison, Jean-Pierre Sanchez, Daniel Braithwaite, and Dai Aoki that has grown the sample from the CA Grenoble here, and Alexander Schick from the Institute of Physics in Prague. So, as I said, the work that I will present you today is the outcome of a long-standing collaboration between 3 teams. The team of the ESRF ID12 beamline, whose responsible is André Rogalev, and the team of Jean-Pascal Brison, Jean-Pierre Sanchez, Daniel Braithwaite, and Dai Aoki, who has grown the sample from the CEA at Grenoble, and Alexander Schick from the Institute of Physics in Prague. So UG2 represents the first example of materials where ferromagnetism and superconductivity coexist, but are not competing. This is an extremely highly studied sample because, as I will show you now, because if you plot, for example, the phase diagram of a temperature as a function of pressure, you can see that as a function of pressure, one observes a crossover from a strongly polarized ferromagnetic phase 2 that carries a magnetic moment up to 1.5 MeV to a weakly polarized ferromagnetic phase, FM1, that carries a smaller magnetic moment of only 0.9 MeV. And what is really exciting in this sample is that the superconductivity appears only in this ferromagnetic phase 1. Now we can also see that this crossover is not only observed as a function of pressure or temperature. If we go now to 14 kilobar, so it's 1.4 gigapascal, we can also observe a crossover as a function of the field. If one starts first with a small field, we are in the ferromagnetic phase 1, which is a weakly polarized magnetic phase. And by increasing the magnetic field, we enter in the so-called, again, ferromagnetic phase 2. This is nicely observed when we plot the magnetization curve as a function of the field and as a function of the pressure. You see there's a metamagnetic transition. The lower plateau is the so-called ferromagnetic phase 1, and the higher plateau is we are in the so-called ferromagnetic phase 2. Now, why are these systems so interesting? It has been shown by previous experimental and theoretical work that these changes or these changes across this ferromagnetic phase 1 and 2 is due to the change of the localization of the 5F electrons. As you have heard from the previous speaker, as a function of the pressure, you can indeed change the number of electron counts. And here it has been highlighted that this may be the change of the 5F electrons may be at the origin of this observed changes across these ferromagnetic phases. Here we would like to show using ZANES and XMCD that it is possible, first of all, to resolve or to see what is the microscopic origin of these different magnetic phases. The question is now, how are the uranium 5F orbital and spin magnetic moment affected across the ferromagnetic phase 1 and phase 2 transition, and what's going on with the electron localization? For that, we have used X-ray magnetic circular dichroism spectroscopy. That is an adequate tool to study the microscopic magnetic properties. Indeed, first of all, it is element specific and orbital selective magnetometry tool. As it has been shown previously, ZANES is sensitive to the electronic structure, to the valence state, also to the symmetry. And using XMCD offers also the possibility to extract the orbital and spin magnetic moment, the relative orientation, and the ratio with extremely high accuracy. So first, to prove the electronic and magnetic properties of uranium in uranium germanium 2, we have to probe directly the 5S state. The absorption edges that are suitable to probe directly with 5S states are the M45 edges. With M45 edges, the M5 edges of uranium is located at 3.55 electronvolt, where the uranium M4 edges is located at 3.72 electronvolt. The quantity to measure, so-called XMCD, is per definition the difference between the absorption cross-section for circular polarized light with right helicity, here in black, and with left helicity. This difference between the two absorption spectrum is the XMCD. You see that the XMCD signal, in the case of uranium germanium 2, at ambient pressure under a field of 1 Tesla and at the low temperature at 2.1 Kelvin, we see that this XMCD signal is very large at uranium M4 and rather small at uranium M5. And also we can see that at the uranium M5, it has a dispersive line shape. Now, with the help of some rules that has been derived by Tolle, Francesco Sete, and Paulo Cara and Gerrit van der Laan, and even by Saras in the early 70s, it is possible to relate the experimental integrated Xanes and XMCD spectra to ground state expectation value of various operators. Indeed, that has been shown before. From the Xanes, it is possible to determine the variation of, for example, of the 5F electron counts, also to estimate what is the number of 5F electron counts, and also to disentangle the number of electron occupancy in the 5-half subshell and in the 7-half subshells. From the XMCD, it is possible to extract the orbital magnetic moment carried by the uranium 5S states, the spin moment, and as well the ratio of the orbital to spin moment with extremely high accuracy. And this is what we wanted to do. So for that, we need a dedicated experimental station that allow us to measure the high pressure XMCD. Here I show you this experimental station that is located at the ID12 beamline. We have a net which is equipped with an 8 Tesla superconducting magnet. The beam is coming from the right side. The cryostat is inserted in the warm bore of the solenoid magnet of the 8 Tesla superconducting magnet. It can be cooled down for sure using a cryostat, using transfer line. We have also the possibility, there is a possibility to measure the pressure in situ. So one difficulty measuring the pressure in situ is not as generally is down, where the PRL system is not close to the cell, so we are 30 centimeters from the cell, so which is already very difficult and challenging to measure the pressure, but it's actually not a problem. But we need also a specific diamond all-mill cell. Since the edges are located at 3.5 kiloelectronvolt, if you use a so-called partially perforated diamonds with a remaining cullet with a remaining thickness size, a thickness wall of 150 micrometers, you see there is practically no transmission. So one had to develop a specific diamond on-mill cell in order to record the fluorescence yield of the sample. For that, we have designed and developed a diamond on-mill cell that combine a fully perforated diamond, completely fully perforated, and associated it with a thin disc diamond underneath. Since this diamond disc can be as thin as 30 micrometers, meaning that the transmission can be as high as 30% transmission squared, we have therefore now a nice diamond that allows us to record the fluorescence yield coming from the sample. So we are the only ones still actually in the world using such a type of diamond cell. What is also possible, thanks to EBS, is that this new type of diamond on-mill cell can reach a pressure as high as 16 GPa. As a detection system, we are using the total fluorescence yield detection in a backscattering mode because transmission is not anymore possible. And also as a focalization system, we are using a two-dimensional barium lenses, which has been shown that even in this energy range are working pretty well and allow us to have even a spot beam size as small as 2 micron vertical and 2 micron horizontal. So let us first show you the Xanes that has been recorded at the images under pressure. Here we have tuned the pressure from 0 kilobar up to 2.6 up to 26 kilobar, this independently of the field of 1 Tesla or 6 Tesla. What we can see directly is there is no spectral changes have been observed at both uranium M5 edges and uranium M4 edges. This means, with the help of the thumb rules, that it is possible using this to determine the variation of the number of 5F electrons, and using a standard is even possible to estimate what is the number of electrons at zero pressure. From this, we show that we have observed that the number of 5F electron is absolutely constant within the pressure range from 0 to up to 3 gigapascal. You see even that in this scale that only tiny small variation of 0.03 electron has been observed. Then we can also disentangle the number of electron occupations that are in the 5-half subshell and the 7-half subshell, and you observe that even this in both subshells there is absolutely the number of electron occupation for these two subshells is absolutely independent with pressure. So it means directly that there is no change in the localization of the 5F electronic states are observed. Now let us go to dichroism, to the magnetism. Here we were able to record very nice XMCD spectra at both edges, M4 and M5 edges under pressure. Here for simplicity, I show you the different spectra that has been collected and for the different ferromagnetic phases, the ferromagnetic 2 phases, which is a strongly polarized phase, the ferromagnetic 1 phases, that is a weakly polarized phase, and even in the paramagnetic state. Just to make you more clear the changes that are observed, all the spectra have been normalized to the M4 edges to a -1. You see that indeed the spectral shape of the M4 is hardly changing. But if I look more in detail into the uranium M5 edges, you see that clear changes are observed as a function of pressure. You see that at ambient pressure, the integral of his XMCD at uranium M5 is negative, while if one go to the paramagnetic phases, the integral of his XMCD signal becomes positive. So it means that with XMCD, we are able to observe subtle electronic changes within the spin orbitals, which are in the vicinity of the Fermi level. Now, using this XMCD spectra, it is now possible, first of all, if one go set the energy at the maximum of the uranium M4 edges, it is possible to record the so-called element-specific magnetization. This is what we have done to ensure that the sample are of high quality and similar to what is observed macroscopically. First, if we go to very low pressure, small pressure, where we are in the ferromagnetic phase, ferromagnetic phase 2, and if you tune this as a function, and if you record this XMCD as a function of the field, you observe a nice magnetization curve that is square, that is really similar to what is observed macroscopically. If we increase the pressure to 14 kilobar, one observes indeed a metamagnetic transition. The smaller plateau is attributed to the ferromagnetic phase 1, while at higher field, this larger plateau is attributed to the ferromagnetic phase 2. And this is exactly similar to what has been observed in a macroscopic. So you see that there is a good agreement between the discrete data magnetism provided by the uranium atoms. If you go to even higher pressure, if you go to 26 kilobar, you see that this transition is shifted to much higher field. So now we have determined the orbital to spin moment ratio for different pressure, for different fields, and for different fields. So this ratio has been determined for different fields, and this is what I will show in the next slide. So first of all, I remind you that we saw no change in the degree of the 5F electron localization. This is this plot here. It is strictly a straight line. So there is no change in the uranium 5F electron counts. Now, if we go to determine the uranium 5F orbital and spin magnetic moment and the ratio, we first found that this ratio, orbital to spin moment, is negative, meaning that the uranium 5F orbital and spin magnetic moment are aligned antiparallel. We see that if we are staying in the ferromagnetic 2 phases, by increasing slowly the pressure from 0 up to 14 kilobar, we observe first that this ratio is decreasing with pressure. Indeed, what is happening is that there is an orbital spin compensation. The spin moment becomes larger, meaning that the orbital and spin moment, the difference becomes closer to a ratio of -1. If one goes now to a smaller field, if we stay now at 14 kilobar, if we ram the field down to 1 Tesla, we are again in the ferromagnetic phase 1. We observe a drop, an abrupt drop of its orbital to spin ratio. If you increase again the field, this is again increasing, and this is perfectly reversible. So to observe a nice abrupt drop at the magnetic field-induced transition from a strongly polarized ferromagnetic 2 phase to a weakly polarized ferromagnetic 1 phase, and this is perfectly reversible. And also, if one continues to increase the pressure, even if the orbital to spin moment ratio is even decreasing further. Now, how can we now understand what our observation? For that, we have performed theoretical band structure calculation using DFT plus U in the orbital polarization limit in order to capture what's really going on at this ferromagnetic phase 2, ferromagnetic phase 1 transition. First of all, we were really happy to observe that within the calculation, we observe a similar effect. Indeed, if you can do the calculation in the ferromagnetic 2 phases, you observe that the orbital to spin moment ratio is as small as -2.nt. If you go to the ferromagnetic 1 phases, you observe indeed a decrease of the orbital to spin moment ratio. For both phases, it has also been seen through the calculations that the number of 5F electrons is not changing at all. So now how can we understand these changes of the orbital to spin moment ratio? For that, we have looked deeper into the calculation, and we found out that there's actually, at the transition, there's a swapping of the electronic population that takes place between only two levels, the levels G5 and the Mg for -1/2 and +1/2. If you are in the ferromagnetic state 2, you see that the occupation, the electron occupation of its sublevels of -1/2 is larger than the one of +1/2. And if we go to the ferromagnetic phase 1, we see exactly the contrary. You see that the number of electron counts is decreasing, where in the case where for the sublevels +1/2, the number of electron counts is increasing. And this small swap electron population is responsible of the moment of the changes of the orbital to spin moment ratio, is responsible for the diminution of the total magnetic moment in the ferromagnetic phase 1 compared to the ferromagnetic phases 2, and but this does not affect at all the electron 5F counts. We believe that this peculiar orbital occupation scheme could be at the origin of the appearance of the superconductivity that it takes place in the ferromagnetic phase 1. So as a summary, we have probed the microscopic magnetic properties of the uranium 5S states in uranium germanium 2 under pressure using ZANES and XMCD experiment. I recall you that these are very challenging experiments because first of all, we had to develop a very specific diamond Alvin cell. We found out that the number of 5F electron count is pressure independent. There is no 5F electron delocalization at all. We found out that the uranium 5F orbital to spin ratio decreases as a function of the pressure. The orbital magnetic moment of the uranium 5F is compensated by the spin. We observe that across the transition between the ferromagnetic 2 and ferromagnetic 1, there's an abrupt drop is observed at the field-induced magnetic phase transition. These experimental findings are confirmed by DFT plus U calculation. And finally, we believe that it's likely that the observed enhancement of the ferromagnetic fluctuation that are in the ferromagnetic phase 1 are also correlated with the different occupation of the spin orbitals between the ferromagnetic 1 and ferromagnetic phases, rather than with the delocalization of the 5F electrons in the ferromagnetic phases. As a perspective, and thanks to EBS, it is now possible to perform high pressure experiment as high as 16 GPa at 2 kV. It means that it is now possible to probe the phosphorus, sulfur, chlorine, potassium, and calcium cages, the LHGs of 4D transition metals and actinides, and the MHGs of actinides. And this is only possible at the ID12 beamline so far. With that, I would like to thank you for your attention.
Thank you, Fabrice. It was really interesting. Me, I have a simple experimental question.
Yep.
When you, at some point, you showed your XMCD spectrum as a function of pressure, and at some point also a larger magnetic field. Are you there? Yes, you're there.
Yeah.
And I saw that the noise increases. There was more noise with pressure, and I was wondering why. Maybe because the sample is thinner.
No, simply, no, we use the same sample, simply we are in the paramagnetic phase. And if you go back to this magnetization curve, you see that we are collecting a signal which is much smaller in the paramagnetic phase. So it's practically 5 times smaller or even 10 times smaller. That's why the noise is increased.
Okay.
This is simply because the signal is smaller.
Okay. And so what you showed was normalized. So because
exactly, because in order to see the differences, I prefer to plot everything normalized. Otherwise,
yes. And then I was wondering which transmitting medium do you use?
We use helium. Helium as a transmitting medium.
Okay. And which other materials, which are the perspective now with EBS? So you mentioned the edges, but do you have in mind the specific materials?
Yes, so we are for sure continuing this adventure or looking at actinide systems, but we are also looking for other systems, magnetocaloric systems that contain phosphorus or even sulfur in petrol systems or geoscience systems. So that could be also interesting, not maybe from the magnetism point of view, but from the Xray point of view. Because since we are the only ones that are able to collect, to perform Xray measurement at those edges.